Hey guys, Lissandro here, and today I'm gonna do another blog. Um, so basically, earlier today was just give me a sec. Man, I hate when this microphone messes up. Okay, okay. So anyway, where was I? Okay, so basically, I'm doing a morning blog, and what I want to talk about is uh, tasers. Okay, and what I want to talk about tasers is that pretty much are they dangerous and can do they have the potential to kill you? Okay, now it all depends your power rating of your taser, because keep in mind these are high voltage devices. Okay, so let me go over to my whiteboard over here and let's take a look. Okay, you guys. So basically, I'm right here at my whiteboard to explain some things over tasers. Now, tasers, you've seen like two types. You have like two prone ear, and there's an electrical arc over here and all. That's one type, and the other one that you probably may have seen is the pretty much the projectile type. That pretty much is propelled by a CO2 tank. Hold on, let me do this. This is what I hate. I can't. You can't really draw right in this type of surface. Okay, there's a tank in here, and there's CO CO2. There's CO2 here, and it blasts two prones that once they get to the target, it sends an electrical current. Now the thing is, there's a huge misconception that people make that it's the current that kills you. It's the voltage that kills you. And the thing is that the misconception people have is that if you have like if you have 1 ampere, uh, let's say 1 ampere of current, that'll kill you. And the thing is, yeah, it will. But the thing is that you need a high enough voltage for that. Okay, is that you see the thing is that in reality it isn't neither the current nor the voltage that kills you, it's the amount of power that kills you, that goes across your body, how much electrical power it dumps across your body, how much uh how much damage it does, because it can kill you in a number of ways. For example, it can kill you pretty much affecting your nervous system and affecting your heart. That's one way. Another way it can kill you dumping a lot of thermal energy in your body that can damage vital organs. Um, there's a number of different ways it can kill you. It can kill you. So in reality, it's the amount of power that it dumps across you. Now, if a lot of you if a lot of you seen like electrical outlets, okay, these like electrical outlets, okay, these electrical outlets usually have um, 120 um, volts AC. Okay, uh, or you probably seen huge outlets like these, that these are usually 220 volts AC. Okay, and these can vary 110 or 240. It all depends, because usually you get like dirty you get dirty electrical output. There's a friend of mine that told me that in some areas you'll get like roughly 180. But this is like very rare. Now I'm not gonna get into R RMS or anything like that, but the thing about these power sources, they have huge amounts of uh, current. They uh, they have huge amounts of current that they supply, because remember, these are directly from the power grid, so they have more than enough to kill you. Now the thing is, how fast does it kill you? Now let me just say one thing. Remember that AC current is a sine wave, okay? And it's is and I'm just covering the 120 volt one. So 120 volts, that's like 240 volts peak to peak. Okay, this is 20 volts. Okay, now also another thing you have to consider um, is that I don't know if you've seen on your cell phone adapters or DC power adapters, it always has something like 60 hertz, and some of them have like 60 hertz angle 0 degrees. Okay, this what this refers to is the frequency of that the sine wave of that AC current. It's the frequency that goes across it. So let's say you have a sine wave, and let's say this signifies 1 second time frame. Okay, so and you have 120 volts and negative 120 volts. Okay, and that means that you have what that means is that you get 60 cycles within 1 second. Okay, so what this pretty much means is that uh, in concept, and in concept, if you were to touch, let me make a sine wave here. If you were to touch an electrical outlet, both positive and both terminals, at the right time that uh, it hits zero, you would not get you would not get electrocuted, because it's currently at that right moment when it's at that right moment where it pretty much there's no current flowing, because it's an alternating cycle. In reality, let me make a better picture here. Okay, in reality, um, there's a certain region here where you can touch it. You can touch it without it killing you or electrocuting it. The problem is that this time frame is very minute, it's very small. So in order for you to touch an AC outlet without it electrocuting it, you would have to be super fast. Okay, because one thing I want to mention is that a lot of the time, um, a lot of the time is the rate of change. Is the rate of change, and that's why in calculus we use derivatives. You use to calculate the rate of change, and that's really important because the thing is that you pretty much measure how much power it dumps on you. And keep in mind also that the frequency, your frequency, how many hertz matters a lot because of two important equations. The first one being XC, which is um, capacitive reactance, which the formula is 1 over 2 pi f, which is your frequency, C. Or you can write it as 1 omega C, which is pretty much the same. Let me correct that right here. I don't know why it's doing that. Omega C. Okay, and the other one is XL, which is capacitive, not capacitive, inductive reactance, which is 2 pi f, which is your frequency, L. Or you can write it as um, omega L. Capacitive reactance and inductive reactance. Okay, and yeah, pretty much here that you all know that one over a large number becomes a small number. So your higher your frequency is here, your lower your capacitive reactance will be. Okay, the smaller the higher the reactance would be, and this here is vice versa. Okay, so you have to keep in mind this, how much capacitance your how can I say, how much capacitance your body has. That's an important factor because we're pretty much we're pretty much a bag of electrolytic fluids, especially our nervous system. So we are conductive. And the thing is that you may say, "What? That how's that possible? How's that even possible if when I touch my outlet it doesn't electrocute you?" And the reason why is because at that power, which is usually like 5 volts 1 ampere, 5 volts isn't enough to cross your body and do serious damage, even if it's 1 ampere. Now, if you wet your hands and everything, you might feel it. It might hurt and all, but it won't kill you, depending on how much time you spend on there. It's the time frame that's important. But it's XL is inductive reactance, and XC is capacitive reactance. And the thing is that when it comes to AC current, they measure impedance with Z. Okay, well, what does this have to do with tasers? Well, the thing about tasers is that yes, they have like ranging from 7,000 volts. As a matter of fact, I have a device that generates this much amount of voltage, 7,000 volts or 10,000. uh, kilovolts, and so on. But you know what the thing about this is? Some of them have as little as 1 ampere, 1 milliampere. Hold on, I messed up again. 1 milliampere or zero point 0.1 milliamperes, or small. They have small amounts of current. Um, another thing is that pretty much, un- remember the rate of change. When they use a taser on you, they're not going to use it for a prolonged amount of time. So they only use it in a short period of time. So if you were to measure the time frame in which they use the taser on you, um, which they use the taser on you, it's not that much power to do serious damage. Of course, this is an exception whenever it comes to people who suffer heart disease or have serious medical problems, which small amounts of electrical current can even affect their medical condition, and that's one thing. But for most normal people, this isn't enough to kill them. However, it is enough to pretty much hijack their nervous system and just disable them. There, however, there's been cases where people have resisted and all, and the reason why that is because different people have different capacitive impedance. Remember the XC, and remember there's two factors going on in your body. Your R, which is your electrical resistance, that's uniform, and your XC, your capacitive um, resistance, and it's variable in every person. So that's pretty much it that I wanted to explain and all. But anyway, um, I guess this will be all for now. Um, anyway, thank you for watching. Um, Please like and subscribe, and I'll catch you guys later.